Yeah, I could put the camera off.
Yeah, you
Anyway,
put
it's
the
not
camera off. Yeah.
working properly.
Okay, so
Wait a minute, sir.
yeah, let's wait for some time, 2-3 minutes.
Pawan, YouTube is not working.
Yeah.
Hello, Pawan. Are you there?
Yes, sir. I'm trying to connect with the YouTube, but
Okay.
recording is in process.
Wait a minute.
Yeah.
Start the recording also.
Recording is started,
Okay.
but YouTube I am just working on it. Maybe YouTube site is slow.
So let us know when it starts, then we can start the program.
Pawan, are you trying?
Yes, sir. I am trying on YouTube, but the link is not working. Just few minutes, sir.
Okay, yes. Otherwise, you'll only record and later on put on it. But some people.
Yeah. Just try once more and then
Yeah.
we will do.
Okay.
Hello, can you hear me now?
Yes.
Yeah. But it's still lagging a bit.
Yeah, that can't be helped. That is anyway the property of Zoom.
No, sir.
Pawan, if it is not working, we can postpone it to post later.
Okay, sir. But YouTube is not working. It's a gateway issue there.
Okay. So, Professor Kate, sir, maybe you can start.
Okay, all right. So
It is getting recorded, right? Make
Yeah,
sure
it's
Pawan.
recorded.
Okay, thanks.
It's recording.
So let me welcome all of you for this online program. Today is the last day of this 1 year long program on Triangle Group, Bailey Uniformization and Modularity, organized at Bhaskaracharya Pratishthan, Pune. The program actually started in September 2021, last year, and it will be ending today, 30th August 22. And the program was held as a trimester program in 3 parts. In total, 66 mathematicians gave talks. There were 95 talks in this year-long series. And out of these, there were 24 Indian speakers, 18 India-based and 6 from abroad. There were 21 European speakers. They were from UK, France, Russia, Germany, Spain, Switzerland, Italy. There were 13 American speakers, 5 Canadian, 2 East Asian from Singapore and Taiwan, and one South American speaker from Brazil. So on behalf of the organizing committee, I, as a convener of the program, wish to convey my sincere thanks to all the speakers who made these events possible. I greatly acknowledge the constant support of the advisory board members, namely Professors Henry Darman, Ravi Kulkarni, Sujata Ramdorai, Dinesh Thakur, and John White. Many topics of the program were related to the work of Henry Darman, Ravi Kulkarni, and John White. Professor Dinesh Thakur and Professor Sujata Ramdorai have been a source of inspiration and guidance right from the initial stages of the program. And it is because of their support that the program could be carried out successfully. My personal thanks are also to Devendra Tiwari, who coordinated the program very well and worked relentlessly for its success. On my personal behalf, I also thank the members of the organizing committee, namely Krishnendu Gangopadhyay and Supriya Pisolkar. And also in the first trimester, there were Jitendra Vajpayee and Chandrashil Bhagwat. All these organizing committee members shouldered various responsibilities, including chairing the sessions. In addition, the coordinator wishes to thank Professor S.G. Dani and Dr. Amala Bhave for their encouragement and support. I thank the technical committee members who worked relentlessly to host Zoom meetings and YouTube live streaming smoothly and with rare glitches. For this, I appreciate all the efforts made by Soumya De, Utkarsha Mishra, Makaranda Sarnobhat, Girish Kulkarni, Pawan Dodya, Ganesh Shyam, and Vaidehi Chattopadhyay. I wish to take this opportunity to thank many mathematicians for the encouragement and appreciation of the program, as well as making themselves available to chair various sessions and helping in this event. There were 22 chairpersons, mainly from India. The program was supported by the Mathematics Consortium under NASI TIMC programs, and it was also supported by National Board for Higher Mathematics. RC Foundation from USA supported it by way of arranging token honorarium to foreign speakers. I thank all of them for their generous grants to meet the expenditure incurred in this program. I also wish to thank the BP staff, the staff from Bhaskaracharya Pratishthan and colleagues at Bhaskaracharya Pratishthan, especially Professor V.M. Sholapurkar and Professor V.V. Acharya. I'm also glad to inform you all that as an extension of this series of seminars, we plan to bring out proceedings for each of the trimesters. Details of these are available on the program webpage. With this, I would like to conclude my few words, and I request Professor Parmeswaran to chair the session. Thank you.
Yeah. Thank you, Professor Katre. It's a great pleasure for me to chair a session here, and that too for the lecture of Kapil. So I really appreciate this Bhaskar Pratishthan's long efforts to continue with the year-long trimester program on triangular groups, daily uniformization and modularity, which went on for the whole 1 year very successfully, and I had been part of it once and I had attended a few too. So thanks for streaming it online and making it really accessible to everyone. Yeah, now I would like to request Professor Kapil Paranjape to present his talk on Calabi-Yau modular forms and Calabi-Yau varieties. Professor Kapil.
Yeah, thanks, Parmu. Yeah, thank you all the organizers for giving me this opportunity to give this talk. It represents, yeah, hello.
Your slides are not available, not sharing?
They should be, I don't know. Let me share once more and see.
Yeah.
Share screen. You have to share the screen again. Huh?
Yeah, coming now.
Yeah, now it's coming.
Yeah, coming.
Yeah.
Yeah. So this talk represents joint work with Dinakar Ramakrishnan. However, as I have mentioned, all the errors are mine. And I do apologize, though I have not really been participant much in the trimester, though the topic was one which I did do some work in when I was working with Dinakar. Unfortunately, the pandemic and so on interfered, and so I have not actually managed to interact with him or with this topic for a few years. So at the same time, I do thank the organizers for asking me to give this talk, and then because of that, I'm thinking about these things again. Right. And I do appreciate a lot the efforts being put in by Bhaskaracharya Pratishthan to have such very high-level conferences and talks. Okay. So let me start with something which is somewhat classical, which is called the Kronecker-Weber theorem. It says that if you have a finite abelian Galois extension K of Q, then there exists an integer nk such that the field is contained in the nth roots of unity. Okay, zeta n denotes the primitive nth root of unity. So you take any finite abelian Galois extension of rational numbers, then in fact it is a subfield of the field of cyclotomic numbers for a suitable nth roots of unity. So now the other point I would like to make here is that the action of Galois group on the roots of unity is well understood. So even if we don't know the explicit inclusion of K in Q zeta n, the above inclusion may not be given explicitly, but still we can deduce.
Have we lost him?
Yeah, his connection was not proper, perhaps. It was coming.
Right, it was lagging quite a bit.
Yeah.
But now he seems to have just gone. Yeah.
Disconnected, yeah. Came back.
Sorry, the situation here in terms of power is very bad. The power seems to be keep going and coming.
Oh,
Okay, so I hope you can see the slides now.
yeah, now it's
Yeah,
coming.
Yeah. So the connection just went because the power went, and I don't know why. The connection should be on UPS, but it's not. So anyway, okay. So as I said, the action of Galois group on Q nth roots of unity is well understood, and so one can use this to deduce the powers of properties of the structure of K up to conjugation, even if the above inclusion is not known explicitly. So the idea is to somehow generalize this for more complicated Galois actions on linear actions. So I won't go into the whole philosophy of Langlands, which says that In fact, one should expect that in many cases this is given in terms of motives. Okay. But let me just say, what is it that we are looking for? So the theory of pure motives provides a semi-simple Q-linear tensor abelian category M. And for each smooth projective variety over Q, there are objects HKX in M for each K. And an element of M is said to be effective. It is a direct summand of HKX for some M. So in general, there may be some twists by linear, by one-dimensional objects which will make them ineffective also. Okay, so the absolute Galois group of Q is supposed to operate on M. And the Kronecker-Weber theorem can be seen by a statement as a statement about the motive associated with the scheme spec K. So that is one way to look at it. And if you go to, so that's a zero-dimensional scheme. So let us see what happens if you look at one-dimensional schemes, so one-dimensional smooth projective varieties. So for a curve of genus G, we get a weight 1 effective motive of dimension 2G. So even though the theory of pure motives as represented in this slide is somewhat conjectural, but for individual objects, individual smooth projective varieties, the motives have in fact been explicitly shown, right? So many of the cases which we'll talk about, the motives have actually been shown to make sense. So there is, and moreover, there is a version of this Q-linear tensor abelian category which has been constructed by Nori. And so one could also think in terms of the Nori motives of a variety. So for many purposes during the talk. Okay. And in his case also, the absolute Galois group of Q does operate on that category. So it is quite adequate for many purposes that we want in this today's talk. Now for a curve of genus G, we get a weight 1 effective motive of dimension 2G. And the classical theorem of Riemann says that a weight 1 effective motive is H1A for an abelian variety A. Right? So in a sense, the role of the roots of unity is going to be replaced by the study of an abelian variety in this case. And we can see that the study of weight 1 effective motives can be reduced to the study of abelian varieties. So rather than studying all kinds of more complicated objects, we have reduced it to the study of a single, not necessarily much less complicated abelian varieties, smooth projective varieties. Right? So we have made a reduction, just like for abelian field extensions, we have reduced it to the study of cyclotomic field extensions. Now, what about motives of weight K for some other K? So, in general, we should expect effective motives of weight K to occur in HK of a variety of dimension K. Right? So, note that the variety also, I'm saying, has dimension K. Okay, it's not just that it is HK, but it's also that the variety has dimension K, and this can be done because of the theorem of Lefschetz, which can be applied to smooth projective varieties. And Lefschetz hyperplane section says that somehow we can cut down the dimension without losing the motive. Okay. So we are looking for HK, and again Lefschetz hyperplane section theorem or some version of this study of motives and an application of what is known as the generalized Hodge conjecture would say that we only need to consider X such that HK0 of X is non-zero. Otherwise, you can expect to reduce the weight. So if HK0 is 0, then in fact the motive can be found to be associated to one which is twisted and which is of lower weight. So you can assume that the weight is, not only that the weight is K and the dimension of the variety is K, and you're looking at HK, but HK0, which is can be also thought of, remember, if you're looking at an embedding of K in, well, if you're taking a field, you're taking rational numbers. So you can think of this as essentially omega K of X. I think I've got it right. Okay. Yeah. In other words, we want to study K-dimensional varieties with non-trivial holomorphic K forms. So this is what we really want, and we want to find some special classes of such varieties which will capture all motives of weight K, all effective motives of weight K. So now let's go to weight 2. So we can attempt to study effective motives of weight 2 via the study of algebraic surfaces with PGS equal to H20S is non-zero. So PG in this case is just an analogy with curves, is known as the geometric genus of the surface. Now, usually when PGS is bigger than 1, we have studied surfaces of general type. This should have been about. So this is a difficult topic. Unfortunately, not much is known about surfaces of general type. So let us, in fact, concentrate on PG equal to 1. And then there is a theorem of Morrison, which shows, assuming a particular case of the Hodge conjecture. So he shows that there's a Hodge correspondence, and the Hodge conjecture will imply that it is actually a correspondence and therefore gives the same motive. There is a K3 surface S or T, so that the non-trivial part of the motive of S is contained in the motive of T. In other words, an effective motive of weight 2 is actually associated to a K3 surface, is contained in a K3 surface. Okay, so that says that we can somehow be interested in. Yeah, is there a question? Yeah. So the main point is that we have brought down the study of effective motives of weight 2 to the study of K3 surfaces. And so that suggests that in general, if you are looking for things with geometric genus 1, then maybe we should be looking at Calabi-Yaus. Okay, so this suggests that we should first attempt to understand the result for what we might call Calabi-Yau type motives. So can we say that if we, so look at an effective motive of weight K such that HK0M is one-dimensional. So this is analogous to the K equal to 2 case, where we are looking at surfaces with PGS equal to 1. And we can ask the question whether such a motive is associated with a Calabi-Yau variety of dimension K. Okay. So this is a variant of the same question, but now we have further restricted our attention to those motives which are of Calabi-Yau type. In fact, of course, we would like these Calabi-Yau varieties with the spelling of varieties, unfortunately, I missed an E, to be somehow explicitly identified, right? So we don't want to just say some Calabi-Yau variety, but in fact, we would like to be more specific about the kind of Calabi-Yau varieties which would arise. Okay. So in order to show the other part of the story, I have to talk about motives associated with Hecke eigenforms. I think this may have already been talked about in some of the talks earlier, but in any case, obviously Calabi-Yau also has been talked about earlier. So modular forms arise in the study of the action of the Hecke operators on the space of gamma 1 n. Of course, for other gamma n invariant, but I'm primarily interested in gamma 1 n. So recall that this means that it's a matrix of the form A, B, C, D, where A and D are congruent to 1 mod n and C is congruent to 0 mod n. Right. And of course, inside SL2 Z. which oxen buffer flame. Yeah. And we are looking at gamma 1 and invariant, equivariant holomorphic functions. So the natural action of SL2Z on holomorphic functions, which is corresponds to the K weight K. So you multiply by a certain factor of holomorphy and look at gamma 1 and equivariant holomorphic functions, and which are eigenfunctions for the action of Hecke operators. So SER constructed L-adic representations associated with such modular forms, and then he generalized this to show that there should be a pure effective motive of weight, it should have said, K-1 associated with the modular form of weight K. And then later, Janssen and then Conrad have written down explicitly. I think there was some slight lack of explicitness in the work of Janssen, which then Conrad filled in. And in any case, they were able to construct an explicit, pure, effective weight K-1 motive MF associated with the modular form of weight K. Okay, so these are the ones which we are somewhat interested in. So now modular form for gamma 1n looks like F tau, which is sigma, the so-called power series at the cusp at infinity, which is an q to the power n, where q is e to the power 2 pi I tau. And when this is a Hecke eigenform, then this can be normalized so that all the ANs lie in a finite extension of Q. And in fact, the AN for a general N can be determined from the APs for P prime, and the latter are eigenvalues of suitable Hecke operators TP. Okay, so there's a very nice arithmetic theory of modular forms, which was developed by many years ago by Shimura, Eichler, and even earlier Hecke and so on. And there's so the main point I want to emphasize here, which is relevant for us, is that all the ANs lie in a finite extension of Q, and we are interested in the case when ANs lie in Q. This is the case. This is the same as the case where the motive MF satisfies HK0 MF is one-dimensional, right? So the condition which we are looking at, what we call Calabi-Yau modular motives, would correspond to those where the ANs lie in Q. And in that case, you say that, we sometimes say that F is a rational eigenform, right? So in summary, we can ask whether the K-1 dimensional Calabi-Yau varieties associated with Hecke eigenforms of weight K, which have coefficients in Q. This is the question which we can certainly ask. Okay, and as I explained, as I will explain now, we would like these Calabi-Yau varieties to be somewhat special. Is there any question so far? Okay. So I want to explain this specialty of what we are asking for in terms of the idea that we want to use this variety somehow to help to calculate these coefficients. So the idea is that somehow we should be able to calculate these coefficients by looking at points of the variety mod various primes. Okay. So the idea is that we can determine APs, and if we can determine APs, then we can determine EM, and APs would somehow have something to do with the number of points of the Calabi-Yau variety. So I would like to, maybe I should have remarked it here already, but I will remark it short when k is equal to 2. Okay, I think it's there on the later slide. So that's where we are going. And so I want to talk about how we are going to associate this modular form to counting points. So it's a zeta function, zxt, so the standard formula which counts points of f over the field with q to the r elements for every r. And following the proof of the Weyl conjectures by Dwork, Groth, and Equerlin, we know that this function looks like a product of polynomials, rational function actually, polynomials to the plus minus 1 powers, where these polynomials are a certain characteristic polynomial associated with a pure motive over a finite field. Okay, so this we know now for a smooth projective variety. And for a smooth projective variety x over q, we associate a similar zeta function by taking the products of these zeta functions, except that we replace the variable t by t to the power minus s, and where we look at the reduction mod p of x. And for most primes, xp is the reduction. There will be bad primes and there's some factors there, so I don't want to bother about those. And I think I've also missed, there's probably some factor of infinity which I'm missing. Okay. In any case, this suggests the notion that suppose I wanted to look at the L function of a motive, a pure weight k motive, then we would like to take it as a product of all primes or most primes, whatever, of the reduction mod p of the motive. And then the zeta function would in fact become the product of the L functions of these motives. So these are standard, what are expected from the tidying up the theory of motives to counting points. Now the left-hand side is obtained by counting solutions mod p, while the right-hand side is in general a complicated expression. So this suggests that in order to understand LMS, which is our main, remember our goal is to understand motives, because we are trying to understand a modular form and we are associated to a modular form of motive, and we are trying to understand the motives. So in order to understand LMS, we should look for a variety, not M, but X, where HKX is somewhat simple motive, except for one K where the motive is M. Okay, so look at this formula. Suppose essentially what I'm trying to say is one of these factors was M and other factors were simple. Suppose we had this behavior, then by counting points on the left-hand side, we could determine the L function on the right-hand side. And the L function, so this is part of the theory that the L function of the modular form is in fact the L function of the associated motive. So that fortunately does not find a place somewhere in what I have written. But the L function of the modular form is the L function of the motive. So in other words, we can determine the L function of the modular form and thereby talk about the coefficients and things like that, provided we can write the motive in terms of a variety which has a rather simple expression in the sense that HK is a simple motive except for 1K where the motive is M. Now, the simplest motives are those associated with H2DY, where every element of this cohomology, so Y is a variety of what is called, where its motive is fully algebraic. So Y is a variety where all its cohomologies are, groups are generated by algebraic sets. In this case, the L function is just a product of, the L function of the motive is of 2dy is just a translate of the usual zeta function. Not to say that it's well understood, but it's certainly well studied. And so we could expect that we can use that to calculate the L function of M. Okay. So let me say, therefore, what is it that we are looking for in terms of speciality of Calabi-Yau varieties? I hope the basic idea is clear, that we are trying to understand the L function of a motive. So we started with a modular form, then we constructed a motive, and we are trying to understand this motive, the L function of this motive, right? And the idea is that that's the same as the L function of the modular form. And that will be used to understand the coefficients of the modular form. Because this L function of the motive would be part of zeta xs, where x has, well, zeta xs actually consists of this one and some of the standard zeta functions with some translates, right? So that tells you that I mean, and this x is an explicit variety. So this we can try to calculate using counting points over finite fields, and so you can use it to determine the L function. So that's the general picture that we want. So what kind of variety are we looking for? So a smooth projective variety can be said to be a simple Calabi-Yau variety if it is a Calabi-Yau variety. So this has been obviously said many times during this trimester. It is simply connected. I think sometimes people drop this hypothesis and simply use the fact that it has no holomorphic forms for R forms for 0 less than R less than dimension X. It has no, and it has a nowhere vanishing top holomorphic form. So obviously, simply connected wouldn't work for the case when dimension X equal to 1, for example. And the additional condition I would like to put is the next one, is that it carries an involution x to x, which acts as -1 on this top form and +1 on the rest of the cohomology. So not only that, in fact, we can go further and ask for the condition that y, which is x mod I, is a smooth rational variety whose cohomology is given by algebraic cycles. So this is the best possible scenario that you could imagine, and it would make things very easy, and you could apply techniques. This has even superior aspects, because we know that when we are trying to take a double cover and we are trying to count points on a double cover, then this is somewhat easy. So we can go further and we can ask for even this condition, that it's a smooth rational variety, and counting points on rational varieties whose cohomology is given by algebraic cycles is again something which is relatively easy. So this is the best that we can ask for, and the question is whether we can do that in some cases. Under these assumptions, the L function of the motive associated with h of dimension x can be recovered by counting points in xp up to multiplication by zeta translates of zeta function. So that's the general idea. So you can, somebody has a question. Is that? Somebody has said they lost the connection.
It is old message. It is old message.
It's all message. Okay. Thanks for clarifying. I was worried that all this talk was for nothing. Okay. Yeah, sometimes when you're giving a Zoom talk, you wonder if there is anybody at the other side. Because I can only see my slides. I can't see the rest of this. Okay. So where was I? Yeah. So let me say what is the main question. Given a Hecke eigenform with coefficients in Q, it is precisely the complement of in h star x of h star y, where y is the quotient of x by this involution. Okay. So this would be the ideal situation, and this would allow us to use geometry and some special geometry to calculate Hecke eigenforms, the coefficients of Hecke eigenforms, and prove various things about them. There are a lot of interesting questions about Hecke eigenforms, some of which are asked by Ramanujan. And so it would be very nice if we had a good control over computing them. Now, by Akle-Shumara theory, when k is equal to 2, we can construct an elliptic curve EF. And an elliptic curve, of course, carries a natural involution such that the quotient is the projective line. So that particular case of k equal to 2, which is always a motivating case, is in fact valid in this context. So this gives the complete solution when k is equal to 2. The next case is k is equal to 4 because modular forms of gamma 1n have even weights. And so we are looking for special Calabi-Yau threefolds. And more generally, of course, you could look for higher dimensional cases. So now let me just state the main result, which was proved by Dinakar and myself, which is that when n is less than or equal to 6, and let k be the smallest one such that there is exactly one modular form of weight k for gamma 1n, then I want to say there is a kx, however, it is singular, but its motive is not singular. I mean, the motive is a pure motive, which is not mixed. So, though it's a singular x, and we tried, in some cases we managed to desingularize it, in some cases we didn't, which otherwise as in the fact that it's singular, other than singularity, positively answers the above question. So in fact, X is birational to the moduli space of k-pointed curves of genus 1, and which again is basically the argument which is used by Conrad and Janssen to associate to X the motive. Right. So the pairs nk for which there is exactly one modular form of weight k for gamma 1n are the following, right? And the theorem applies to the first row but not the second row, because you can see that it's not the first, right? I mean, here is this one, here is this one, here is this one, here is this one, and this number is bigger than what we have, right? We have not yet figured out what to do for n equal to 7. Okay. So these are the cases where one can do this. So actually there are finitely many cases and one can do it essentially case by case. Note that the dimension is 3 in this case, 3 in this case, 5 in this case, 5 in this case, 7 and 11, right? So we are looking for, so in the first two cases, desingularization is relatively straightforward and we could do it. And in 5, we could make the singularity of rather small large codimension. But in 7 and 11, we could not even, you cannot do that much about the singularity. So that's the status of the work. Okay. So in other words, the second row is one worth working on, because we have nothing to say about this particular row, and certainly one of them is a threefold. So we can ask the question: Is there a Calabi-Yau threefold which has this particular modular form? We also have some other results which are in the paper, which are about modular forms with complex multiplication in Ziegler form, which is also has a similar flavor, but I don't want to get into that. Okay. So I just want to look at quickly in one slide. I want to just look at the idea of the proof. Okay. Yeah. So I just have another 4-5 minutes. I will wrap up. So let X be a smooth projective surface and W be the subspace, be a subspace of the space of anti-holomorphic forms. on the smooth projective surface. So we are looking at a surface which is like a rational surface, like P2 or something, right? Which has a lot of anti-holomorphic forms. Rather, whatever, I suppose anti-holomorphic is not the right word. Whatever, dual space of holomorphic forms. And this gives a linear systems of curves on X, and note that because they are sections of negative canonical bundle, these are actually of genus 1. Now assume that W is of dimension n. So this n should have been k or something earlier. And assume that P is birational. So this is just a statement, I mean, which requires in each case the explicit S and R are given in the paper. But basically, what the idea is that P is birational to the modular space of ESR, where E is a curve of genus 1, S is a collection of mark points on E, and R is a collection of relations of these among these mark points, in the sense that some divisor made up of some of these points is equal to some other divisor made up of some of these points, and so on. So some such collection of some such linear system of curves on a surface. And then on Xn we have a natural map from W tensor. Xn is X cross S n times. You have a natural morphism from W tensor OXN to the direct sum of Sorry, I got disconnected again. So I was talking about a smooth projective surface and a linear system of minus k of the surface, which is of dimension n plus 1. N, okay. Dimension. The linear system is a dimension n minus 1. And then we are looking at the linear system as consisting of certain marked elliptic curves, or actually certain marked curves of genus 1. And then we look at on the product of the surface with itself taken n times. We have a natural morphism of vector bundles of rank n from W tensor OXN to the direct sum of the pullback of the anti-canonical divisor from the inline bundle from each of the factors. So this is morphism of two vector bundles of equal rank. So we can take the determinant, and the determinant is a divisor which parameterizes tuples of the form ESR, P1, P2, Pn, where P1, P2, Pn are points on the curve, and which is, because of the construction, this is the determinant of the left-hand side is trivial, determinant of the right-hand side is minus kx. So from the adjunction formula, you'll see that you get a variety with trivial connective. And basically the idea is that you can start with this variety and you can desingularize it by using various properties. And that's the way in which the construction proceeds. So I think I'll stop here and maybe I can take questions if there are any. Yeah.
Thank you. Thank you,
Can you
Kapil.
hear me? So
Yeah.
I'm
Kapil, can you
ready
hear?
to take questions. I don't have anything more to add here.
Yeah. Hello, Kapil, can you hear? Can you hear me? Devendra.
We can hear you. We can hear you.
Okay. Yeah, I don't know whether
I don't
Kapil
know
could.
about Kapil.
Yeah, I don't know. So now it's open to questions.
He got disconnected at this moment. Maybe he will join.
Just wait. But anyway, anybody has some questions? So we can, so they can unmute and ask, right? Everybody?
Yeah.
I got disconnected again. I'm sorry. Yeah, you had a question?
Yeah, so far none. But I do have one if there is nothing else.
Sure, sure.
Yeah. Kapil, you gave the fourth condition on construction of Calabi-Yau.
Right.
Yeah, that's about two-sheeted covers, right? Of rational varieties.
Yeah, right,
So
right.
it looks like you start with a rational variety and the branch locus has to be, I believe, it has to be a smooth divisor. And
Smooth
it's
divisor
probably
and
from K inverse or K to the
K
minus
inverse. Yeah. From
2. K
K
inverse or
inverse.
K to the minus 2?
K inverse.
Yeah. So a smooth section of K
No,
inverse
maybe
and
you're
that
right.
produces.
K to the minus 2. You're right. So
Yeah, that's what I thought. Yeah. Because you need 4 points, no, to give away from P1.
yeah, correct. Yeah.
So my question is like, can you really sort of list them as which rational variety and the K to the minus 2 section give rise to a Calabi-Yau?
No, so I mean, as such, if you take a section of K minus 2 and you take a double cover, of course you will get a Calabi-Yau, right?
Always.
The question is which ones come
extra,
associated with
there's no
modular
extra
forms.
conditions needed.
No, not always. So that's the question. That's the question, is turning it around. The question from the geometrics can be, in what situation would you get a modular form? Can you hear me?
On every Calabi-Yau, you may not have an involution, no?
Pawan, can you mute Professor Kulkarni? He's talking to someone else and he's Pawan, are you there?
That's why I'm saying that you're looking at those which arise as double covers, and you can ask. Calabi-Yau has an involution. So I'm saying that on the other side, we are looking at those varieties which arise in this double cover fashion, and we can ask under what conditions. So basically, there are rather special sections of K minus 2K, which will give rise to modular forms. Okay. So in the case of genus, I mean, in the case of dimension 1, in every case we get when the 4 points are such which are defined over rational numbers. I mean, the quadratic equation is defined over rational numbers. We get a modular form, right? So that is the theorem, if you like, in the of Wiles-Taylor, which says that once the variety is defined over Q, it's an elliptic curve defined over Q, then it's associated to a modular form. So it's not expected that that question will be very easy to answer, as you can expect, as you can see, right?
It's more to do with arithmetic than geometry.
Yeah, so that has to do with arithmetic. So we are trying to turn arithmetic into geometry, not the other way. That is more difficult. Yeah.
So in other words, you need to give the condition on the divisor, right?
Yeah, no, actually what we want is we start with the modular form and somehow we want to exhibit this variety in somewhat explicit way so that we can count the points and things like that.
Oh.
So
Okay,
you have
which
to
means-
actually somehow do some construction with moduli spaces of marked elliptic curves, which will give me the moduli space of, which will give me a space in which the motive will occur. But now I have to extract from that motive somehow this Calabi-Yau variety. Okay, so there's an explicit variety and I would like to do some quotienting and group actions and so on to extract a Calabi-Yau variety.
So for that, you first extract the rational and then take the double cover, or?
Yeah, so yeah, exactly. So you would try to find a quotient which is rational and then try to see that there's a double cover sitting somewhere in between.
Okay. Yeah, thanks. Any
At
other
least
question?
in the examples that we have, that works.
Okay, yeah.
But in general, it could be more complicated.
So there, what kind of group you get? You take the Galois group or something. It's not the. And
No,
this
so there are all this permutation group. I mean, at least in the constructions which we are doing, there are all these permutation group actions and so on. So you can use those.
And the Calabi-Yau is in between. That's a
And
double
the
cover.
Calabi-Yau is in between somewhere, which factors through. Yeah. I should have mentioned one more thing. You see, there's one construction in modular forms which is twisting by quadratic characters. The nice thing is that with this double cover, that twisting by quadratic characters can also be understood in terms of in geometric terms, because twisting by a quadratic factor has a meaning in terms of doing, when you have a double cover, how do you take the square root? So over complex numbers, there's a single square root, y square equal to fx.
Correct.
But over rational numbers, you can put a y square equal to fx for different a, which are not, which may not be has square roots, and you will get twists, quadratic twists of the variety, and that will correspond to quadratic twists of the modular form. So we have not only constructed the modular form in the case of a fixed, the variety in the case of a fixed modular form, but also for the twists.
Okay.
In this case.
Yeah, thanks. So any other questions? As Suri said, people could also type on the chat. Yeah, so if there is no more questions, so let's thank the speaker. And I'll hand over to Devendra or Katri. Yeah.
Thanks to you, Professor Parmeswaran, for coming to chair the last talk, and you chaired the first talk also of this trimester.
Yeah, thanks.
Okay.
Okay, so thank you, Professor Paranjape, and thank you, Professor Parmeswaran. And it was nice. The whole thing went on very smoothly with the cooperation of many people, as I already said. Anybody wants to express anything? Professor Kulkarni wants to say anything, or Tendu or Devendra, you want to say anything? Otherwise,
No.
Yeah, okay, all right. So the program is off now, and this whole program, trimester program, is over now, and the proceedings of this will come out, and managing editor for this is again Devendra Tiwari, and he, with the help of other experts, he is trying to bring out these proceedings, and more information will be available on the website.
Maybe we will keep sending some emails in between for some.
Okay, so yeah, thank you again. Then now we'll stop this program. Okay, thank you.
Phone, stop the recording and YouTube.